Everyone, and welcome to my latest video. Today I'm looking at how the fragmentation patterns, that's the peak patterns that you can see in a mass spectrum, relate to your molecular structure. So if you'll recall, in my previous video I explained how mass spectra are formed when molecules are bombarded with a string of charged particles, usually either electrons or positively charged ions, and that effectively smashes the molecule to pieces. And the molecules tend to break along weak points in the molecule. So strong bonds tend to stay together and the weaker ones tend to fracture off. Now it can be quite complex. We're going to look at some fairly simple options. But in general, the masses of the different fragments that are formed can give you an indication of the structure of the molecule. So we're going to start with alkanes and generally alkyl chains. So within most molecules, there is a carbon chain of some description. It could have methyl groups or ethyl groups or propyl groups, branch chain groups, whatever, and those tend to show up on our mass spectrum. So the sorts of common fragments we might see, if we've got a long carbon chain, you could see a CH3 group, you could see an ethyl group, a propyl group, a butyl group, and they have distinctive masses. So anytime you see that kind of pattern where you've got peaks of mass to charge ratios of 15, 29, 43, 57, that will indicate these 1, 2, 3, and 4 carbon groups. What that means is that there's a piece of the molecule which contains that many carbons attached together. Now, the other thing to note is that tertiary fragments, so that's where you've got a carbon that's attached to 3 other carbons, that group will tend to stay together. It won't fragment up very easily, but it will break off quite easily. So you'll quite often see a tertiary fragment or a secondary fragment existing on its own, because they tend to kind of put more strain on the molecule, so they tend to split off a bit easily. Okay. So on the shared drive is this infographic, and it does show what some of the common fragments may relate to in terms of the atoms present. It's not the greatest diagram in the world, but it can be useful, so feel free to have a look at it sometime. But in the meantime, okay, so let's start with a really simple alkane. We've got methane. Methane has a molar mass of 16, which means its molecular ion peak will be 16. Okay, there we go, molecular ion 16. If it loses a hydrogen, because it's only got carbons and hydrogen, so the only way it can smash up is to lose a hydrogen, then the fragment that is left has a mass of 15. And so you would end up with a peak also at 15, as you can see there. Methane's not the most useful example, however. Let's think a little bit further. If we have a look at propane, propane has a molar mass of 46, no, something like that. And you can see when you look at the mass spectrum that the molar mass, there you go, 44. My math is not very good at this time of night. Molar mass of 44, and you've got a molecular ion peak there at 44. You could lose a hydrogen, give you a peak at 43. You could lose an entire CH3 group, which will give you a peak at 29, and we can see that quite clearly there. Anytime you have a difference between the molecular ion peak and the next largest ion of 15, it usually represents the loss of a methyl group. Okay, so let's have a look at something a little bit bigger. We've got pentane. Molar mass, 72. Molecular ion peak at 72. We will lose the methyl group, molar mass of 15. That's going to give us a peak at 57. We could then also have another fragment which splits off the next bit, and so we could also have a peak at 43. We could have a peak at 29 and possibly even a peak at 15, although one doesn't exist here. And so that kind of characteristic pattern with peaks at 29, 43, 57, sometimes 71, that indicates that we have this progressively increasing carbon chain length, or rather that we have a long carbon chain that's broken off into a bunch of different fragments. So here you can see it even more clearly with heptane. The molar mass of heptane is 100. We lose 15. We're down at 85, lose another 14. So losses of 14 typically indicate ethyl groups. CH2 groups, not ethyl groups, CH2s. And so we come down to 71, 57, 43, and 29. 43 is often a really common base peak, both because it's a 3-carbon group, which you can see happens quite commonly, but also because you'll often get that as a branch chain group. So anytime you've got, you think you might have something with a 2-methyl type group on your carbon chain, that could indicate that you might be looking for a 43 peak in your mass spectrum, because that CH3 group is going to give you a mass of 43, and it's quite stable, so it tends to stay together. Now with alcohols, we have our OH group, and that has a mass of 17. The other thing you have is a CH2OH group, which sometimes you will see also, and that has a mass of 31. So that common fragment of 31 represents a CH2OH. So in this molecule, the molar mass of ethanol is 46. We can lose a hydrogen, we get the peak of 45. So that hydrogen off the OH is often an easy loss off an alcohol. We could lose a CH3 group, and there's a peak at 31. So that's what I'm talking about with the CH2OH group. So if you see it peak at 31, that's a common fragment. And we could have an ethyl group, so we lose the OH, and that gives us a peak at 29. So those peaks at 29 usually indicate an ethyl group. Peaks at 31 would represent a what we call methoxy group, so CH2, that's methyl with an oxy group. So those can be some key ones to look for. And we see a difference of 15 between the molecular ion peak and the next one down. That represents usually the loss of a methyl group, and a loss of 17 would be the loss of a hydroxyl group. So here we have our propanol, kind of similar. You can see there again that peak at 31, you can see a peak at 29, you can see a peak at 43, and you can see a peak at 59. So the molar mass is 60, which will give you your molecular ion peak. Lose a hydrogen, and that's your 59 peak. Lose the OH, and that gives you your 43 peak. That's your propyl group, 3 carbons, that 43 peak yet again. If you take off the ethyl group, so you've got again that CH2OH group, then it'll give you your peak at 31, and your CH3CH2 group will give you your peak at 29. So again, you're looking for that difference of 17, which could be your OH group. You're looking for other parts of your fragmentation patterns as well. Butanol, let's see what we see again here. Yes, there's that 31 peak yet again. Okay, so butanol, molar mass of 74, so there's our molecular ion peak. Take off 1, and we've got our peak at 73. So you can see that pair of peaks down at 73 and 74. We can lose that OH group, and that's going to give us the strong peak at 57, okay, which is a 4-carbon chain. We can lose a propyl group, and that gives us that peak at 31 again. Okay, that propyl group in itself gives us a peak at 43. We've also got peaks at 29 and at 15, which are your CH3 and your CH2CH3. So all of those peaks are present there. Very characteristic with an alcohol and a straight chain alcohol. If we had butan 2-ol instead of butan 1-ol, then we could not have a peak at 57. Why not? Well, I suppose we might be able to get a peak at 57, but we certainly wouldn't get a peak at 43, and we wouldn't get a peak at 31. If you look at the structure carefully, you'll see why it's impossible to get a peak at 31. Okay. So the more we look at the structures, the more we become familiar with it, the more information the mass spec can tell us. It is a matter of familiarity. It is time consuming to get used to it. Mass spec can be very complicated, I should say. Aldehydes also give us some information. So that fragment at 29 represents that chunk. And so that can be an interesting one. The trick with a fragment at 29, though, is it can also represent a CH3-CH2 group. So it's not as useful as some other things. Okay. With a ketone, though, you almost never get a fragment of 29 unless it's in a longer carbon chain. Okay. But a peak at 43 in this case is going to indicate that loss of a methyl group. So that's going to be your CH3 C double bond O at 43. So 43 again is one of those fragments that can mean multiple things. So please don't be fooled by saying, oh, it's got 43, it must be a ketone with a methyl group attached to it, or it must be 43, it's got to be a propyl group, or something like that. There are multiple ways that you can make up a peak of 43. Similarly, there are multiple ways that you can make up a peak at 29. Esters are more complicated again. Okay, but again, if you've got a peak at 29, that could indicate that the double bond oxygen is at the end of the chain. And particularly with esters, the key thing is that they often fragment in the bond between the carbon, or between the carbonyl group and the single bond oxygen. So through this fraction here, if you can see where my cursor's going, I don't know if you can or not, but that's a common fragmentation point for a ester. It can give you some idea about the masses. You can also obviously get the loss of your alkyl chains. And you get those fragments forming. Esters are more complicated, but again, if you have a look, again, the loss of the carbon chains and particularly the loss of the carboxyl chains, so the ones with the carbon chains attached to the single bond oxygen, that tends to be where the split happens, where the most common fragmentation point is. So those are some of the key functional groups that we will see in this topic and some of the fragmentation patterns for them. It does get quite confusing. I will post some more information as we go along. But right now, I hope this gives you enough to start looking at a bit further. I will see you soon. Thanks for listening. Bye.